Good morning, 8th of December. We've now come to problem 20, which seems to be doing the analogy of lemma 1 on page 59. And I was afraid that we would skip to page 60, doing the analogy of the, well, never mind. When I studied lemma 1, I understood it, of course, but it was like an ant creeping along the ground. Often I feel like a hawk above the field, seeing other possibilities, etc. This way it was, I could understand it, but I didn't feel I would be able to do the same thing in another situation. That's what we have to do now. So we have chi3, one of the two non-trivial characters of exact order 3. The trivial one has order 3 as well. And then prove that, okay, so we have to look at. That will be formula 3 on page 57, which I should have written that in advance, of course. I'm not sure it's this one, but let's see. And it works if chi2 is distinct from chi1 bar. And that's the case if chi1 is set to, or chi2 is set to chi1, then they are distinct. Now I'm having problem with notation because in formula 3 here, chi1 and chi2 are arbitrary. Up here it is one special one. And then chi3 squared, that must be the other guy. We have this, and chi3 to the third equals unity. So it should be pretty obvious that so let's see what we can do here. I would like from this to prove that chi3 squared equals chi3 bar. Oh, pretty obvious. We multiply this with chi3 bar, and then it's chi3 squared, chi3 bar equals chi3 bar. There we are. Oh, I forgot to put the microphone in place. Sorry about that. right. Then what do we know? Yep. Well, it's time to multiply by we take this equation and multiply by we extend this with g of chi3 forget this for the time being. And then we have formula 2. This is chi of -1 times q by formula 2. But -1 is a cube. So it's unity. We just multiply by q. That was A. Now B. So this is the lemma 1. I'm sorry if you can hear, we've just had an Indian moving in besides me, and he tends to scream a lot or shout when he talks. So we have to prove that 3 divides 1 plus j chi3 and set extended with square root -3, or q, the integers of q extended with square root -3. So I'm trying to repeat what I remember from the proof. It's the sum and all of these are units. So that means that they lie so it's a unit, and that was that it's not in the module extended by square root minus 3. We're probably going to use exercise, what was the number? I just checked the number here. Exercise 18b. So my first question is, do we have an A so that this gives unity? And when we can pair them, will that give a, anyway go oops, J of 1 with itself? I believe we had a formula for that. No, we don't. Of course we don't. I'm thinking whether we could use the same trick and take out those where 2a equals unity. There's only 1/2, and otherwise they are paired. Well, let's try that. I don't know if it will lead to anything. So first, when a is 1/2, oops, plus, and then we just sum half of them. And this, of course, equals chi3 of 2, so it squared. So it's, oh no, take it easy, son. It's chi2, I'll just do it. It's chi3 squared, 1 divided by that of 2, and that's 1 divided by, or chi2, now I just say chi bar squared of 2, and oops, is that chi3 squared of 2? I need to do it thoroughly. I'll erase it afterwards. And then we multiply it by chi3 barred What about multiplying it by, oh yeah, chi3 of 2, chi3 bar of 2. There we are. So I'm trying to repeat the argument of of lemma, whatever it was, lemma 1, I think it was. So this is congruent, or this is, yeah, multiplied by some unit times 1 plus, or lies in there, yeah. So this one, that's silly. It's congruent to 1 modulo 3 times some unit. And this is as well. So it's just congruent to 1 modulo a unit. The product is just congruent to 1 modulo a unit. Well, as I see it, I need now to show two things. The first one is that chi of 2 equals, it should be equivalent to minus 1. It can't be. No. At this point, I may need another trick, or maybe find out how to carry on from this. So this is where I'm stuck, as I expect it to be, feeling like an ant. A little report before going to lunch. I played some piano, and then I looked at it again, and then I noticed something. If we look at this ideal generated by square root minus 3, and then multiplied by the units, minus omega bar times omega, and minus then you see that 1 omega and omega squared all are equal, lies in 1 plus this ideal. Square root minus 3. Oh, this minus should be in there. never mind. So I'll correct that afterwards. So that was just a little notion, so now I'm going to lunch. Having had lunch, I'm looking at it again. Apart from this, I just note, I've corrected this of course, I noticed that the number of atoms here that are non-zero is q minus 2, and that means that it's equivalent to q, it's equivalent to minus 1 modulo 3. And connected with the notion that all the products of the unit of omega, powers of omega, is equivalent to 1 modulo square root minus 3, and the number of atoms is equivalent to minus 1 modulo square root minus 3. We have that J itself must be equivalent to minus 1 modulo square root minus 3. But we are not yet quite finished. We have some more solutions being equivalent to minus 1 modulo square root minus 3 than modulo 3. Hello again. 2 days gone. It's evening, December 29th. I got stuck, so I did what I usually do. Worked on some examples to find out how stuff was added when we compute J. I took Q equals 7, and first we needed to find out the primitive character. So we take a primitive root, that's a generator of the multiplicative group, and make the exponential map with x point y, so that when we sort it, we get a table of the log, that should have been log 3 of course, in F7. And then we can define the one non-trivial character. The other one is the complex conjugate, by simply looking up, say when we take chi of 2, we look up here. So that's a square, and therefore we put omega we square omega. And of course, if x is naught, then the result gives naught. I define the procedure. Doing the same stuff, and it only works with prime numbers as I've programmed it. And then we find out how the different powers combine. So a equals naught gives naught, a equals 1, the second one gives naught, a equals 2, that was omega bar and 1, etc. I did the same for 13 and 19. And the idea I had already yesterday was to work on the sum and write it up explicitly, not knowing exactly which combination of the different powers of omega we would be dealing with. So I took the example from 13 and counted it. Oops. There we've got it. And this gives nothing. 2 gives 1 and omega. That's a bar there. 3, omega, omega, mark there. Omega, omega bar, we mark there, etc. We notice that the sum gives 3 here, a minus 1. Oh, it's r minus 1, sorry. And that's because they are the values of chi are evenly distributed upon 1 omega and omega bar. However, when a itself is unity, then 1 minus a vanishes, so chi vanishes. So that's r minus 1, and the others we get r times. And of course they are symmetric, as already pointed out in the book. The ones in the diagonal are mostly even, 0, 2, but one must be odd, and it comes here from chi squared of 1/2, chi of 1/2, so it's chi squared of 7. Let's see if that's true. 7 omega, omega, that gives chi. No, that gives omega. Once again. Omega bar squared, that gives omega. Right. So one of these guys, x, y, and z, is odd, the other two even. I keep writing and j plus I plus z gives r. And now j itself, there we can take the diagonals. The first one gives x times 1 plus, and then the ones, why is this not diagonal? 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So I guess there was only one here. Just erase that. That's omega times omega bar. That gives 2i plus, and 1 times omega, omega times 1, that's 2k, and z. And omega squared only comes from the reverse diagonal here. So Friday, I didn't think I could get anywhere with this, but then this morning I realized that omega minus omega bar equals square root minus 3. So let's try and see what happens if we set omega bar outside. So what do we do here? So we subtract the guys here, and then we have to add them here. No, is that sensible? Let's do that. So that's J. Well, that's it for tonight. I'm getting a visitor. Good morning, December 10th, 9 o'clock. Now let's take a look at what I was doing here. I've come to think that this is very poor tactics. This complication where there shouldn't be a complication. It's a very simple computation, so keep it simple. We are working in the ring, which is a Z module, spanned by 1 and omega, and the ideal is of course spanned by 3 and 3 omega. So let's reduce it to, let's forget this and just reduce this to the basis 1 and omega. 1 and omega, that means that we must do away with this term, and for that we have this relation. So we get x plus 2y minus 2j plus z plus 2k minus y minus 2j omega. And let us do away with x, y, and z. We have these equations here too, where we can just isolate them. I'll write it. So x is r minus 1 minus j minus k minus y minus 2j plus z r minus I minus j plus 2k minus I, that's r, that's y we are working on here, plus k minus 2j times omega. So the r's cancel. Let's do them simultaneously. And the j's minus 3j minus 3j. That sounds good. Why don't I do the i's first? That's really silly. Well, now I've done it this way. So 2i plus I, that's 3i, and the i's here cancel. And then k, 2k, that's 3k. And up here, it cancels, and 3k. So this actually lies in minus 1 plus 3 in the ideal generated by 3. I hadn't expected this method to work. You see, there's no explanation why it works. It's just the mechanics that gives us the result. So we prove it all right, but afterwards we don't know why it must be so. Let's try to use the same method with the fourth order character, of course. And do the same. So how did I do it? Chi of A, maybe 1i minus 1i, and chi of 1 minus A can be 1i minus 1 minus I. And the numbers in the diagonal, we need 6 up here, uv. That's not a good one. J, K, L, M. And in the off-diagonal terms, let's use B, C, D, E, F, G. Oh, there's only G giving I. That doesn't really. Oh, it's 1 here, there's no diagonal term. And then I, there's no diagonal term. To B, 2D, 2E. Interesting. That was the telephone. All right, let's do the same. First the R's, minus, plus, minus. So there were 3 guys, KLM, so that gives minus R, all right. And then the B's, plus B, this really doesn't seem to give anything. That's very interesting. And then C, minus 1, minus 2 C's. And E, that's plus E. And minus D minus G. Oh my God, what's cooking here? Plus 2F. It appears that this method does not work with the quadratic character, but it appears to work with the tertial, what you call tertic character. Okay, so we have finished with problem B. I don't like this because it's the mechanics, all right, but we don't know why it must happen. It just turns out to happen. To happen. And since there is analogous theorems for 2 and 4, it would be nice to have a common explanation of why it absolutely must be so. And I can't deliver such an explanation. So it's not really a nice proof, but it's a formal one at least. This is take 2. The first take, I neglected to turn on the sound. So we'll try it once again. I had the feeling that a dub over wouldn't really work. first D, in the first take, I had no idea what was the problem here. This is obviously a character, and it's obviously non-trivial, so that I couldn't see what the problem was. But let's look at it. We have a set modulo p, let's call that set p. And there we have, it's a field, so we have 3 units. What is it? 3, it's still the morning, so I don't think I'm quite awake. 3 cubic roots of unity. And then we end up, extending with omega, and then here we have a number 11, so we can a number p, so we can create the ideal generated by p. How about this ring? And the next guy is in this in set extended by omega, p, or rather the ideal will, now it is a primary, it does have unique prime factorization, so, and it's the principal ideal domain, so p itself will, let's just say p itself factors. And let's write A as m plus n omega. And B is actually the conjugate of A. Now up here we have the map x maps to x in, and then it's p minus 1/3, so that means p is equivalent to 1 modulo 3, and let's call this guy A, B, C, D modulo p, where d equals p minus 1/3. That was the notation. And of course this guy works in this ring, obviously, and then it projects to this ring simply by taking this ring modulo A modulo P. This is A is an ideal in set extended by omega. A prime ideal even. So what could be the problem? We know that the result, or if we call this F, the result to the third, this unity, So that is the image satisfies the cubic equation here. How many solutions have we got? Up here, we've only got 3, or we've got exactly 3. Down here, we've got exactly 3, because this is a field. So there are at most 3 solutions. And since we know the 3 solutions, unity, omega, and omega bar, then we are home safe. I couldn't really see the problem, but then it appeared to me that up here we have a lot of solutions. So the solutions in XP if we have an x in ZP, so that x to the third is 1. This is in XP, in ZP. Then omega x and omega bar x are other solutions. And there will also be some that is equivalent to -1. And the same thing, we also have minus omega x and minus omega bar x. Maybe there are more, but down in this field, it's a field, there are only 3. So I didn't see the problem, so that's what I had to say about question D. Now we come to E. I started looking at this equation and then taking the modular or is it P? Now it's Q. I don't want to write that number 3 anymore. And let's skip the and then we take the modular. And the modular of G equals square root Q. So that's Q to 3/2. So the modular of J is square root Q. Meaning J must be, and we know, I have to say something here, we know per definition that J lies in Z extended by omega, because the products that we add to get J all lie in here, because the result of the character does. So that means that J itself must be one of the 6 units times square root Q. Now, what was the question? Oh yeah, this gives a circumspect proof that square root Q lies in set of omega. That's a long way. We'll just check it using the quadratic extension here. See, does it have a solution? NFQ. And the discriminant is 1 minus 4. So we must look at the symbol. And then Q is a prime power. I will just take it. Let's do it step by step. Of course, if R is even, then this gives unity. Let's do it step by step. We need to use reciprocity here on each of these. So let's take R outside. Now the reciprocity, we have this is equal to 3 modulo 4. And can we turn it around? That's the question. If P is equivalent to 1 modulo 4, then we can turn it around, and then this gives plus 1. And on the other hand, it's equivalent to minus 1, then this is minus 1, and this gives minus the opposite. So it's actually just this guy, 1 times that. And that means if P is equivalent to 1 mod 3, it gives 1. And if P is equivalent to minus 1 mod 3, it gives minus 1. So it agrees with, as I expected it to, with the quadratic symbol. Or quadratic, I should say. All right. Now, we also know that J is equivalent to minus 1 modulo what? Modulo 3. So what did we have to show? Oh, this is problem E. I don't see that we need to use D. I really don't see it. I think we've just solved it here. On the other hand, if we have the ideal and use the map here, this lies on the real axis, and that means that this ideal should hit one above or one, both one above and one below the real axis. So do we really have an element in this ideal giving both plus and minus omega? So it's generated, let's check that, it's generated by this one, and then I think it is A and B being positive, so we divide by omega. That's A divided by omega. So it's B minus A minus A omega. Are we able to make a z-linear combination of these where the coefficient gives 1? And of course we are. We must have A and B being mutually prime. So there are H and K so that it gives unity. So there actually does exist points in the lattice that allows it all to work out. I've actually thought this before. So I also got the idea that we were able to write out the x value. So that should give us a combination or a connection between the square roots of q in... Oh, it seems that I have a loose connection in the camera here. So this has happened a few times. I have and the third powers of, or the powers that we get using this map. Let's try that. So we can apply this to the generators as a whole. So the, it should be minus A here. So we get this by K, and the other guy minus H. Oh, that's actually annoying. That's really annoying. We multiply by H. this gives omega, and then we have k minus h a plus h times b plus omega. And HA minus HA is minus 1 minus KB. I don't think there's any reduction. Maybe there is some interesting reduction, but I didn't get a relation between the square root of Q in Z extended by omega and the cubic roots in FQ. I did get a relation, but not something that seems interesting at all. All right, that was what I had about problem 20.